During the process of ventricular depolarization, multiple depolarizing vectors of differing magnitudes are moving in many different directions throughout the duration of the QRS complex. It is important to have some understanding of how these depolarizing forces interact to produce the QRS morphology observed in a given lead. In the simple model shown here, an ECG lead is facing two pieces of ventricular myocardium of different mass and differing patterns of depolarization. The lead analyzes depolarization in the plane of the screen. The two pieces of myocardium depolarize at exactly the same time. The mass of muscle in the larger section is sufficient to generate a voltage of 1 millivolt, and it is traveling through the muscle in the plane of the screen at an angle of 30 degrees off the direct line to the lead. The depolarization voltage generated in the smaller section is 0.6 millivolts, moving away from the lead at 63 degrees off the direct line. What is the magnitude of the deflection produced in the lead? Well, if we let the direct line to the lead define the x-axis, the positive signal generated from section 1 is 1 millivolt multiplied by the cosine of 30 degrees. This works out at 0.87 millivolts, while the negative signal is 0.6 millivolts multiplied by the cosine of 63 degrees. This works out at 0.27 millivolts. The total depolarizing signal recorded by the lead is therefore 0.6 millivolts, a positive overall signal producing a strong OR wave of 6 small squares in our model readout. Now consider a second lead sensing these events 30 degrees anti-clockwise from lead A. We let the direct line to this lead define the x-axis, and the magnitude of the positive signal is 1 millivolt multiplied by the cosine of 60 degrees, giving a value of 0.5 millivolts, while the negative signal is 0.6 multiplied by the cosine of 33 degrees. This also computes at 0.5 millivolts. Therefore, in the direction of this lead, the positive and negative vector components from the depolarizing muscle segments are equal in magnitude and no deflection is produced. The readout in this lead is said to be isoelectric. Although significant depolarization voltages are present under the lead, the pattern of flow is such that the total vector generated has no net effect in its direction. In a third lead, positioned 60 degrees clockwise from lead A, these events produce a deflection with a very different morphology. Depolarization of both segments is traveling within 90 degrees of the lead. The positive contribution from the larger section is 1 millivolt multiplied by the cosine of 30 degrees, or 0.87 millivolts, while the smaller section generates a positive voltage of 0.6 multiplied by cosine of 57 degrees, or 0.33 millivolts. This gives a total positive deflection of 12 small squares in the readout from this lead. We can place leads at various points around the origin of the depolarization signals, and using the same simple maths, we can predict the readout in each of these leads. Note how the pattern of flow in these two pieces of myocardium in this simple model produces a distinctive pattern of deflections in the leads. Change the angles of flow of depolarization, and the pattern in the leads will change accordingly. In reality, of course, depolarization events are not all occurring at precisely the same time in different regions of the ventricles. It will help you later if we consider this in our simple model. Look at this situation. The larger section depolarizes first, producing an OR wave of just under 9 small squares in the readout from lead A. The second smaller section depolarizes shortly afterwards, producing an S-wave of approximately 3 small squares. In the lead said to be isoelectric in the first situation we analyzed, the morphology of the model readout is now very different, with an initial positive deflection of 5 small squares generated from the larger section, followed by a negative deflection of the same magnitude. Although the morphology of the readout in this lead is very different from the first situation we considered, it is still giving us exactly the same information. The fact that the positive and negative deflections add up to 0 indicates that the depolarization events taking place under the lead, whatever their magnitude, are flowing in a pattern such that their total vectorial sum is 0. The readout in this lead is still said to be isoelectric. The difference in morphology merely reflects the fact that the negative and positive components relative to this lead are now slightly separated in time. In this model, the morphology of the readouts in the remaining leads remains very similar to before. While the model complexes enclose the same area on the ECG paper, a reflection of the total voltages generated, they are widened due to the delay in the signal from the smaller section. It is also very useful to note that we can use the parallelogram rule to add vectors graphically. Two vectors may be added together by placing the initial point of one at the terminal point of the other. The total vector generated by their addition, shown here in black, is represented in magnitude and direction by a vector drawn from the free initial point to the free terminal point. In our simple model, when we use this technique to add the two vectors together, we note that the total vector generated is traveling at 90 degrees relative to the isoelectric lead, and therefore has no magnitude in its direction, while it is traveling well within 90 degrees of the strongly positive leads. As we'll see throughout the rest of this section, by applying these simple principles to ECG analysis, we can detect alterations in the pattern of flow of depolarization in the ventricles and changes in the structure of the cardiac chambers. As an example of this sort of analysis, look at the frontal leads on this ECG. Observing an isoelectric QRS complex in lead AVL, we can conclude that in this patient's heart, if we add together all of the ventricular depolarization vectors occurring in the frontal plane throughout the duration of the QRS complex, the total vector generated has no net magnitude in the direction of lead AVL. The total vector must be traveling at 90 degrees relative to that lead. This gives us two possibilities. As lead 2 lies at 90 degrees relative to AVL, the total frontal vector may be traveling towards lead 2 or traveling directly away from it. But look at the morphology of the QRS complex in lead 2. It is strongly positive, with a tall R wave indicating that depolarizing forces are in the main traveling within 90 degrees of this lead. Therefore, option 1 must be correct. The total vector generated when we add together all frontal depolarization vectors must be traveling towards lead 2. Consistent with this, the QRS complex in lead AVR is strongly negative, with a deep S wave and little R wave activity. The direction of the total frontal QRS vector is called the cardiac axis, and we've just estimated its position based on the morphology of the QRS complexes in the frontal leads. the so-called hexaxial method. As we'll see shortly, the cardiac axis is determined by the pattern of flow of depolarization in the ventricles, and this in turn is determined by an intact ventricular conducting system. Combined with a little anatomical knowledge, we can diagnose disease by detecting shifts in the position of the cardiac axis. We'll now explore this area in more detail in the videos which follow.